Here's a brief introduction to sequences, very much paralleling section 11.1 in our book. I want to tie it to the financial stuff that we're doing, although there's certainly many more applications to sequences. But let's think about a very simple situation. In fact, the situation of simple interest. We haven't really thought about simple interest very much, but it provides a very simple example of a sequence. What we're going to do is we're going to start with $1,000, and then whoever they are, the bank, will pay us 10% of that, of $1,000 every year. And they're not going to pay 10% of what we have in the bank. They're going to just pay us 10% of $1,000 each year. In other words, $100. So one of the main thing that makes this different from how we've been thinking about it before, we've been graphing things as if they were these functions that are interesting at all possible times. But this isn't really that interesting a situation. We start at $1,000, and then the next year we're going to have a certain number, and the next year we're going to have a certain number, the next year we're going to have a certain number. So it's really just something where we put in an integer, 0, 1, 2, 3, 4, and then we want to spit out how much money we have in the bank at any point. And so that's going to be a sequence. Let me do a table here. Let's say with just 2 rows and a bunch of columns. And so, let's say the year number is n, and let's say the amount we have, we're going to say a sub n. And so that's going to go from, let's say 0. It's actually a good place to start with 0 here when we haven't gotten any interest at all. Let's say up to 9. So here's year 0, we have that $1,000. Then in year 1, we've gotten 1 year worth of interest, so $1,000 plus $100 of interest at $1,100. Then we get another $100 of interest, $1,200, another $1,300, another $1,400, $1,500. Ooh, it's going to be too wide with this magnification. You get the idea. Okay. So this idea of a sub n, it's really a function. So here a, or if we want to decorate it with its subscript, is a sequence. And that really means a function whose inputs are just integers. We're not going to actually try to make sense of a sub 1/2 or a sub pi or something like that. And it's still a lot of the concepts, basically all the concepts we know about functions still work here. It's just that some of them aren't very interesting. And there's some things we can do with sequences that are somewhat unique to sequences. But it's still important that it's a function. But you can also think of it as just what a sequence sounds like, a list in a certain order. And it's just a list of these numbers in a certain order. And what we're doing here is listing all the amounts in the bank account in successive years. Now, can we get a formula for a sub n in this case? Well, this guy looks like it's growing. We know it's growing the same amount every year, so it's a linear function. If we actually thought of this as an f of x, this would exactly be a linear function. Well, in fact, let me go ahead and show a graph of that. To graph a sequence, we can just put dots. It's like graphing a function. It's just that usually we would plot these dots and then we'd connect the dots with lines. But here we're saying, well, we're not going to attach any meaning to things in between. But you can still plot it as these separate dots. And what we see is it's 1,000, and it's definitely growing in a straight line manner, progressively upward. So we could look at our usual ways of finding functions. Well, a sub n, we want an mx plus b kind of thing. Well, it's going to be like mn plus b. B is just going to be where it starts out. We know that one. That's 1,000. And what's the meaning of m? It's the slope. It's how much it goes up each time, and that's 100. So there is a formula for a sub n. And just like functions, it's often useful to have formulas for these guys. But some of the sequences we're going to deal with, they're not easy to get a closed form formula, some sort of simple algebraic expression that always gives you the value of a for every n. one thing that's nice here is what's called a recursive formula. And that is, how is a sub n related to a sub n minus 1? And that actually gets more at the heart of this idea of simple interest. Suppose I knew a sub n minus 1. Suppose I know I have $1,300 in the bank at year 3, and I know I'm getting $100 of interest every year. Well, I don't actually have to go to this master formula. All I have to say is, okay, in year 3, let me do an explicit example. In year 3, that's how much I had in, or let's see, I guess I said year 3. So in year 4, that's going to be how much I have in year 3 plus $100. And in year 5, that's going to be how much I have in year 4 plus $100. Well, that's a general rule. What we can do is we can say, let's say an plus 1. That's any number plus 1 is the amount I had at the number n, at year n, plus 100. And this is true for all n, as long as it makes sense, let's say greater than or equal to 0. Now, I should say, when I say for all n, I really should really say for all integers n. But if we're working with sequences and we're using n, that's really supposed to be suggestive. Letters from the middle of the alphabet are supposed to suggest integers anyway. So often you'll see people drop that integers, but that's really the real thing. So here's a very important fact about this simple interest problem, and it just mathematically says that I get $100 extra every year to transform the amount I had in year n to the amount I had in year n plus 1. Suppose you only told me that. That's the only thing we knew about the amounts in the bank account. Could we recreate these numbers? Think for a second about whether we have all the information we need. If I just say I get $100 a month and my bank account is growing $100 a month. Well, not quite. We also need to know where to start. And for example, here I happen to count starting at year 0 because it was convenient, because that's after 0 payments of interest. And here I need a starting value. So that's the idea, the general idea of a recursive formula. If you know how the n plus first term of the sequence relates to the nth term, and you know where to start, then you know all of the terms. So in fact, that relates back to compound interest. Suppose I have a really nice situation. I start with $1,000 again, and I have 100% interest. Yeah, that's nice. Annual interest. And it's compounded annually. And so it doesn't really make sense to ask what happens in January or March or June or on June 21st or something like that. In other words, to put non-integer values in for the year, just makes sense to put in integer values. So let's redo this table. I start with 1,000. In year 1, I get 100%, exactly all of my stuff as interest, okay, all my money. Then, since it's compound interest now, I get all of that again because it's 100% interest. Now it's doubled to 4,000. Then it doubles again to 8,000. Then it doubles to 16,000. I keep putting it too many zeros, sorry. Then it's 32,000. That is pretty nice. So that would graph like this. Now here, notice it seems like I'm starting with 0. Well, that's because if I go out to 10, which I let this program go out to 10, it is going so high that it's up to 10 times 10 to the 5th. It's over $1 million at 10 years. Now this is unrealistic financially, but I wanted to do a simple one to start with. And we know about exponential growth, which this is. That's really hard to picture, so you can have an accurate graph here and an accurate graph up here. We know that semi-log paper, for example, or semi-log graph would actually do much better, but let's not worry about that right now. So that's the graph of this thing. Well, what about the two kinds of formulas? Well, that's exactly the kinds of things we were doing before with this, with compound interest. Let's start with the recursive formula, because that's really at the heart of the idea of compound interest. And that says that in the n plus first year, if n is this year, then I want to predict next year, so I put n plus 1 here. And that's going to be a sub n times 2, because I'm doubling every year. The 2 is from the 1, which is they leave your money alone that you already had, and then another 1 for the 100% interest. Okay, and I need the starting value as well. a sub 0 was equal to 1,000. So I've got the start, or the seed, you must sometimes call it the recursive formula, or the recursion, and I've got the recursion relation, which tells me how to get the next, and so on. Now, we could have written this. You'll often see the n put here. Suppose I want n to mean the next year, the one I'm interested in. Well then, what would the previous year be? I'd have to subtract 1. Those two formulas look different, this one and this one, but they really have the same information. N is what's called a dummy variable here. It's just a temporary variable that says, I'd like to know what the relationship of any year to the next year is, and I just need a name. Here, I name this year n, and the next year comes out as n plus 1. Here I name the next year n, and this year comes out as n minus 1. Doesn't really matter. And so these two lines here define exactly the same function. But sometimes we want a closed formula, something where we can say, okay, I'd like to know a sub 10 right off the bat. I'd like to plug it into my calculator. The only way directly using this thing would be, okay, well, a sub 10 is 2a sub 9. Okay, well, if I knew a sub 9, well, a sub 9 is 2a sub 8, and that's 2a sub 7, that's 2. And you'd have to string that all out. Basically, you'd have to recreate this whole sequence term by term by term by using this rule, doubling every time, and then stop when you get to the end. And we know there's a more sophisticated way to write that. The closed form is when you double repeatedly, we know a sub n is going to be 1,000. It's just the standard formula, 1,000 times 2 to the, let's see, does n work? This can be tricky sometimes. It might be n plus 1, n minus 1. The way I've set it up, starting at 0, it actually does work, because 2 to the 0 is 1, and I haven't started doubling yet, and so that works. That's something that doubles every time and starts at 1,000. Now, I started with these two examples because, let me go back to the simple interest example. So simple interest, linear growth, and the one way to say this recursive formula is the difference between A3 and A4, for example. Oh, shoot. That's not good. A4 minus A3 is always 100. Well, that's 100. A5 minus A4 is 100. In fact, AN plus 1, let me just stick it in here. AN plus 1 minus A sub n, that's always the same number. And let me pause this. And so the difference between any two successive terms is the same number. So with a constant difference, linear growth, that kind of thing, that's called an arithmetic sequence. It's a really good, not arithmetic, it's arithmetic. It's the emphasis on the met. And so that's going to be a very important kind of sequence for us. It's really going to be not hard. It's just linear growth all over again. Now this guy, compound interest, what's special about this guy is that the ratio, remember when we're thinking about exponents and logarithms, that kind of stuff, we compare things not by taking the difference, we compare things by taking the ratio. Well, this says an plus 1 over a sub n is always the same. And so we have a constant ratio, and that is called a geometric sequence. Those are the two most basic kinds of sequences that we're going to talk about a lot. Now, of course, with the interest example, it would be more realistic to do something like maybe 10% interest. If we go back to this graph, that's growing really, really fast. A more realistic example is something like this, where we start from $10,000, and then maybe we have 10% interest, and we end up with only about $2,600 at year 10. But it's still going to be the same idea, and I just chose a simple number to start with the two. So that's enough for an introduction to sequences, as long as you also read section 11.1.